Chemistry is so hard. How's the valence bond theory and orbital? Wait, the fuck are you? The god of chemistry. The hell? Matter? Skadoosh. Where am I? You're in the chem lab, dingus. What? Chem lab? And I'm here to make you a chem lord. So? No, not this again. Skadoosh. My name is Xavier, and today we are gonna deal with the valence bond theory and sp hybridization. Okay, so what is the valence bond theory? The valence bond theory describes the formation of covalent bonds from the overlap of two different atoms. Because of the overlap, it is highly probable that a pair of electrons are found in a region or space where the orbitals overlap, particularly on the red region shown in your screens. Now, when overlapping happens, two types of bonds can be observed: a sigma bond or a pi bond. A sigma bond occurs through head-on collision between two orbitals, while the pi bond occurs through side-to-side collisions. Sigma bonds are relatively stronger when compared with pi bonds, hence, pi bonds are easily broken while sigma bonds aren't. There can be only one sigma bond between two particular atoms in a molecule, but there can be a maximum of two pi bonds between two atoms in a molecule. Why? This is because when there's a single bond, there's one sigma bond and no pi bonds. If there's a double bond, there's one sigma bond and one pi bond. And if there's a triple bond, there's one sigma bond and two pi bonds. Take note that initially, sigma bonds are the first ones to occur, so it is not physically possible to not have a sigma bond. Now, presence of pi bonds keeps the corresponding atoms in a plane. Increasing the number of pi bonds will increase the electronegativity and the percentage of p character of the bond. Now, although the valence bond theory is perfect for the qualitative description of the shape of bonds, it failed to correctly describe the actual properties. And that is why orbital hybridization has been created. Okay, so now, what is orbital hybridization? Orbital hybridization, or basically hybridization, is a concept of mixing atomic orbitals into new hybrid orbitals, suitable for the pairing of electrons to form chemical bonds in valence bond theory. Now, the hybridization theory was first developed by chemist Linus Pauling in 1931 to explain the structure of simple molecules such as methane. Pauling pointed out that a carbon atom forms 4 bonds by using 1s and 3p orbitals, so that it might be inferred that a carbon atom would form 3 bonds at right angles and a 4th weaker bond using the s orbital in some arbitrary direction. Now, to further explain the importance of orbital hybridization, let us take carbon for example. The normal carbon configuration is 1s2, 2s2, 2p2, or more simply something like this one. The valence bond theory suggests that carbon should form 2 covalent bonds resulting in CH2. But apparently, experiments show that CH2 is highly reactive and cannot exist outside of a reaction. So, how does CH4 aka methane exist? And this is where orbital hybridization comes in. The 2s orbital and the 3 2p orbitals of the carbon atom will merge into 4 identical orbitals called the sp3 orbital. Now this makes much more sense since this will create a more stable and a non-reactive substance as compared to the unhybridized counterpart. There are 3 types of sp hybridized orbitals depending on the number of bonds. First, the sp3 orbital. sp3 hybridization can explain the tetrahedral structure of molecules. In it, the 2s orbitals and all 3 of the 2p orbitals hybridize to form 4 sp orbitals, each consisting of 75% p character and 25% s character. The frontal lobes align themselves in a manner shown in the picture in your screens. In this structure, electron repulsion is minimized. Next, we have the sp2 orbital. Now, sp2 hybridization can explain the trigonal planar structure of molecules. In it, the two s orbitals and two of the two p orbitals hybridize to form three sp orbitals, each consisting of 67% p and 33% s character. The frontal lobes align themselves in the trigonal planar structure, pointing to the corners of a triangle in order to minimize electron repulsion and to improve overlap. The remaining p orbital remains unchanged and is perpendicular to the plane of the three sp2 orbitals. And lastly, in the sp orbital. Sp hybridization can explain the linear structure in molecules. In it, the 2s orbital and one of the 2p orbitals hybridize to form two sp orbitals, each consisting of 50% s and 50% p character. The frontal lobes face away from each other and form a straight line, leaving a 180-degree angle between the two orbitals. This formation minimizes electron repulsion. Because only one p orbital was used, we are left with two unaltered 2p orbitals that the atom can use.